Okay, so what I have here, and I'll give a link to this in the blog post, is a paper that's up at the University of Texas at Austin's website, and it gives a slightly different equation for the for an ellipse. It's 1 minus this epsilon and 1 plus epsilon on the top instead of p over q.
Yeah.
And so I'm gonna make, when we do our graph, I'm gonna make the p's and q's related that way. I'll make p be 1 plus epsilon. All right.
Okay.
Alright.
So here's the epsilon values for the various different planet orbits. So Mercury, for example, is 0.206. So let's go here and make this be 0.206. Oh, actually, you know what?
I think you can just type it in.
We'll go to 0.3 with steps at 0.01. Okay, so 206.
I think, yeah. You may.
Yeah, how do you think I can just type it in?
Yeah, I think you can just type it in there.
And I'll make this go to 2 steps to 1, so 1.206. Oh, close enough. All right, so this is what the orbit of Mercury looks like. So what do you think? Is that a particularly elliptical orbit?
Not really.
It's kind of like a. Might be slightly elliptical, but.
You can definitely tell that it's not a circle, but
Yeah, you definitely can. I'll put in the velocity, and so we can see where there we're getting the velocity and acceleration a little bit wrong, because the acceleration should always be right at the origin.
Yeah.
So you can see Mercury's orbit. You would definitely have to make adjustments if you were thinking it went around in a perfect circle.
Yeah.
Now, if I go back, let's look at the Earth. Oops, wrong. That's the Katherine Johnson paper. The Earth, we've got 0.017.
so it's pretty low.
Okay, so why don't you put that in up here for the
The Q?
for Q? Yeah, 0.017.
Wait, so.
7. Okay.
Alright.
And then this is going to be 1.017. 0.017.
Okay.
Okay.
So
now
you can barely tell. You can see the acceleration's off by a slight amount.
Yeah. Why don't I zoom in?
Yeah, just very slightly.
Just barely. So the Earth's orbit is much more circular,
Yeah.
especially compared to Mercury's. But still, if you assumed it was a perfect circle, you can see.
You'd have some inconsistencies.
Yeah, and so it means the Earth is moving a little bit faster when it's closer to the sun and slower when it's further away from the sun. Now let's just take a look at one more planet. You pick whatever one you want.
How about Jupiter?
So 0.048.
0.48.
Okay, so what do you think is going to happen here with Jupiter?
So we'll have a bit more of an ellipse than
0.048
Earth, but less than Mercury.
and 1.048 for the p-value.
So yeah, we can see that we are slightly off. You can tell that it's not quite a circle.
Yeah, it's not quite a circle. Oh, good point. So it's 1 over here and then a little bit less than -1 over there.
It's
And
like
you can
1.1.
you can see the acceleration vector
Yeah.
is diverging from the origin. And so you would have to make adjustments.
Mhm.
And again, it just means that you have to adjust that the angle isn't changing at a constant rate. Or in calculus language, d theta dt is not constant. And that's really the tricky thing. If I go over to the Katherine Johnson paper, one of the things they're talking about in this paper, they have a picture of it in the end. Let's just find it. So you launch a satellite, and it gets out to some radius r1,
Alright.
and it has what's called here a velocity at burnout. So you turn the engines off, essentially, or they run out of fuel or something. And then from that point, you're at some distance with some velocity, and you're going to end up on an ellipse.
Cool.
And that's so they, in the movie, the calculations that were being shown on that blackboard, which are in this paper, are just this polar coordinate form of the ellipse. In fact, if you go back to the beginning of the paper, there it is right there, what we were just talking about. R equals P over 1 plus epsilon cosine theta. Pretty cool, huh?
Yep.
Wow, yeah.
So it's not just that these parametric equations are, you know, fun and just kind of an interesting topic on their own. Like if you're talking about planet orbits or satellite orbits, launching satellites, things like that, or what this movie Hidden Figures was about,
Yeah.
these are the calculations that were happening in those movies and in real life and in space. Neat, huh?
Yeah.
All right. Good job, guys.